Okay, good morning, everyone. In our last class, we covered the three basic part on syntax analysis. Uh, that is what is called ambiguity and ambiguous grammar, what is called left recursion, and how a left recursive grammar can be converted into a right recursive grammar. And the third segment was how a grammar to be left factored. Now we will be looking into some more aspects before we switch into either top down or bottom up person. Correct? Okay, let's start. Okay. Now, uh, as you know that the main purpose of syntax analysis is the generation of a syntax tree. Perhaps you can remember in the very fundamental class I explained what is called syntax tree. So lexicon analyzer was generating the token and syntax tree was based on some production rule. Like for example, already you have seen that just I'm scrolling up that when some production rules are being given, from that you are forming a tree, correct? Either by following leftmost derivation or rightmost derivation. This tree actually termed as syntax tree, correct? The same thing here we are projecting. Now, in the syntax tree, here let for example some grammars are being given which have Vn, sigma, p and s. Right. Definitely the grammar had a set of production rules. Now the production rule P1 and P2 was there, right there. Based on that, I can formulate a language, correct? So from the grammar, I can formulate a language. That means grammar to production, production to language. Also, you can tell in that way also. Now, let's assume that production rule, which I have mentioned here, I will be using those production rule to design some strings. Strings, for example, you've seen S1 and S2 two strings I have taken. So I don't know that whether S1 does belong to L and subsequently to G or not. But I'm assuming that I have to design a tree, or I have to accept this string S1 for the grammar L by the help of this production rule. Now let my S1 string be this one, 9 minus 5 plus 2, correct? So for this string, I can have the tree architecture like plus can be here, minus, this is a 2, 9, 5. So if I project the node perpendicularly over a plane, so it will be 9 minus 5 plus and 2. So here the expression is being realized. So minus is coming here and plus is coming here. Or even I can start with this architecture as well. 9 minus 5 plus 2. Here plus is coming to the bottom part, minus is coming to the upper part. Right. Now, the two scenarios we are looking at here. One scenario we are looking at Okay, so we were discussing on this part that here the minus symbol is here and plus symbol is here, and here plus symbol is coming to the lower part, minus is coming to the upper part. Now for the string that I have taken 9 minus 5 plus 2, to realize this string I have used the production rule P1, P2 or P3 it may have. By using the production rules, I have formed this tree or this tree. I'm not talking about the leftmost derivation or rightmost derivation. But here, if I ask you to evaluate the tree, that means find out the value of this expression, 9 minus 5 plus 2, it means 4 plus 2, which cumulatively comes 6. Fine. Now, here, if I ask you to evaluate the tree, then definitely you have to approach from top to bottom or bottom to top. Bottom to top. Why? Because if I ask you for a tree, this tree, how many child nodes are there or how many nodes are there? Then you have to approach from top down manner, because this is a root, it has two child, this left child has two nodes, the right child also has two nodes. So in this way I can calculate how many nodes are there. So top down approach needs to be followed. When I am following a bottom up architecture, to evaluate a value of a tree, we need to follow the bottom up evolution. So here the priority of minus is greater than the priority of plus, because I need to evaluate 9 minus 5 first. So 9 minus 5 means 4. Here 4 plus 2 means 6. It is giving 6. Now for this tree, 5 plus 2 equal to 7. 9 minus 7 equal to 2. You check that the results are quite different. Here it was coming as 6. Here it is coming as 2. Correct. So my intention here is to project two different objectives. First is that the priority of the operator you can check over here. The operator which is coming in the lower part should have a higher precedence than the upper part operator, because I am evaluating this is first, so this is a high precedence operator. Here plus has a higher precedence. Though results are coming different, this is a problem with the production rules that I had taken. So the production rule contains some erroneous part. That's why to different architecture I am getting, but it should not have. If it is giving 6, definitely it should give you a 6. Now, the first objective is the priority of operator. You can define which operator has a highest priority. Now, if I assume that instead of 2, I was getting 6. And here the priority of minus is greater than priority of plus. Here priority of plus is greater than priority of minus. In that scenario, if someone asks you for the grammar that you have taken, for this grammar, each gives high importance to which operator, plus operator or minus operator. You are getting a contradictory results, but the outcome is same, 6. Then you will tell that plus and minus will be having the same priority. Let if for this string S1, 9 minus 5 plus 2, if you had obtained only a single tree, let this tree you are not obtaining, only this tree you are obtaining, then you can tell the operator minus has a higher precedence than the operator plus. So if you are able to get a confirmation that only one tree is designed where this operator is coming first, then the next operator is coming second, then the first operator will be having the higher precedence. Right? I hope this is very simple thing you can remember. So this was one portion from the precedence of the operator. Okay. Now one more architecture you can check. Here I have given one more example. Example number 19. E2 is star F, or F2 F plus E or F, and F is generating ID. So you can consider it is a division operator also, as per your because asterisk is there, so division is there. So as per your wish, you can judge it. For this grammar, which has this production rule, What is the precedence of the operator asterisk and division? This is a question. Now S1 string you have taken ID division, ID star ID, for example. For that you have ID division, ID star ID. So division is coming first, so that means division will be having the higher precedence than star. In the same way, you are getting another tree, ID division, ID star and ID. Here the star is having the higher precedence. So in that scenario, you should have said that asterisk and division operator both are having equal precedence. Again, in the same thing I am repeating, if you are not able to get this tree, then only thing was there, division operator was having the higher precedence than the asterisk operator. So the division operator was having the higher precedence than the asterisk operator. Correct? If contradictory results are there over the production rules, then you should say that both are having equal precedence. Okay, this is one part. Now we are talking about the operator, correct? Now one property we have seen, the precedence of the operator, right? So we know that whether the plus has higher precedence or asterisk has a higher precedence. We know that plus has lower precedence than asterisk, correct? So these not our assumption. These are the rules are fed in the compiler. That means these rule means the production rules. These production rules are governed by a grammar. So this grammar is being fed to a compiler on which you are making the codes. Because in the code, it may have a symbol 2 plus 5 asterisk 5. So the compiler need to understand that 5 asterisk 5 need to be evaluated first, then 2 to be added. We know who has the higher precedence, who has not, but compiler needs to be equipped with. To equip the compiler with that knowledge, we need a grammar, and that grammar needs to be fed to a compiler. Okay. So one part we have covered, that is called precedence of the operator. Another part is there from the operator perspective, that is called associativity of an operator. Associativity means, I am writing x equal to 2. So that means 2 is assigned to x. Correct? I am moving from right to left direction. Or even when I am multiplying 2 into 2, I am moving into left to right direction. So 2 into 2 is an operator that I am making. This operation I am making from left to right. This assignment operation I am making from right to left. Correct? Now, here I can tell from which is done from right to left, that is called right associative operator. So equal sign I can tell that it is a right associative operator. This asterisk symbol, I can tell this is a left associative operator, because every operation I am performing, we are looking from left to right. Now, if I consider this example given in question number 20, that x is generating x or y, y is generating z, x nor y or z, and z is producing it. Right? Now, x is producing x or y. If I take a sample string, again, for all the examples, that for these are the production rules, correct? It is associated with a grammar. Our question is given that find out the associativity of the operator XNOR and XOR and XNOR. This is the question. Find the associativity of the operator XOR and XNOR, or it may be a different notations, correct? Now, how to find it out, the associativity property? We need to check the inclination of the operator with respect to a tree. For example, if I start with x to x XOR y, here I have started x to x, here I have started x XOR y, correct? Now x can be expanded to y, so, or even x can be expanded to x XOR y. If I expand it to x XOR y, this is x XOR y. Then x can be, this is the parent production from which I have to start. X can extend to y, X is generating Y. Y can generate Z, or Y can also generate Z X nor Y. That is also a possibility. Correct. Now, if I consider that Y is generating Z and ID, then you check that the operator plus this, this XOR is inclined to left. That means I can tell that XOR operator is left associative. Instead of Z to ID, if I had considered Y2, for example, Z X nor Y, correct? And again, you can check that Y again can be expanded to Z X nor Y, Z X nor Y. Again, Z can be expanded to, not Z, it is Y. Can be expanded to Z X nor Y. So every time it is expanded to, once I'm expanding, it is inclined to right with respect to the previous operator. So this XOR is inclined to right. This is also inclined to right. So that means the inclination is in right direction. I should say that this operator is right associative. And the XOR operator that I have taken here, that is left associative. Correct? That actually some more design I have given here to make the internal things more clear so you can follow it. Okay. Now, what are the areas that we have covered? One aspect we have covered, that is the precedence of the operator. Another aspect was the associativity in operator. Correct? Now, these 5 fundamental parts will be requiring while understanding the parser. One is ambiguity. The another part is left recursion, right recursion. Third is left factoring proportion. Fourth is operator precedence, and fifth is associativity and operator. Correct. Now directly I am coming to the main part of syntax analysis now. Basically you see, let me zoom out the screen here. Basically you see the parser is classified into 2 segments. The syntax analyzer actually classified into 2 segments, either top-down segment or bottom-up segment. Top-down means, as I said, if a expression is given to you, -2, here is 5, here 2, then to evaluate the tree you need to approach in bottom-up manner. But if a tree is being given, how many child nodes is being created, then definitely you need to approach from top-down. So you can assume that based on that ideology, either top-down or bottom-up, 2 different approaches are being inferred. Correct? So under top-down, 2 main categories are there. One is called backtracking category, another is called non-backtracking category. Correct. So bottom-up part we will be covering later. Correct. We mainly will be highlighting on top-down parts here. Now, there was a problem in the backtracking segment. That's why most of the actually the main preference to select a parser was to non-backtracking parser. Correct. So top-down, when I am approaching in top-down manner, then either I have a choice of backtracking or non-backtracking. If a backtracking I am following, then it has some certain limitation. We'll be looking into that. So we are approaching towards non-backtracking. Non-backtracking has 2 categories. One is recursive descent, another is non-recursive descent. So our interest will be on non-recursive descent, which contains LL1 grammar. So what is LL1? That we will discuss later. Here you need to understand that top-down parser is our main focus. Backtracking has some limitation. That's why we have moved to non-backtracking part. Non-backtracking has 2 categories. One is recursive descent, another is non-recursive descent. We need to focus on this non-recursive descent part. Correct? Now, first we are taking one example to understand what is top-down and what is bottom-up. Correct? Here top down and bottom up. To make you understand and to get a more clear idea, consider the following example. Let there is a grammar is there. This grammar has Vn, sigma, P and S. Let these are the production rules, correct, for this grammar. I have to realize a string. Let the string is given S1, A, B, B, C, D. This is a string. So one options I will be having, I will approach to form the tree from top down. So S is the parent variable from which I need to start. S is generating small a, capital A, B and E. So here I am starting S to small a, capital B and E. Then capital A can be expanded to capital A, B, C. So it can be expanded to capital A, small b and C. Then capital A again can be expanded to small b. It is expanded to more small b. And this capital B here can be expanded to D. So it is expanded to D here. If I project all the nodes perpendicularly here, perpendicularly here, I will be getting the value A, B, B, C, D and E. That is the expression, right? Now to get this string from this production rule, I have followed a top-down strategy. Correct. Now, what is the bottom-up strategy? Had I written this form, I'm writing again here. Had I written the string first, A, B, B, C, D and E. This is our objective to get. Right. Now, what first I am doing, you know that capital A can generate B. So I am moving from bottom to up. So capital A can generate B. So here the arc is there. Capital A can generate B. So backtracking method I am approaching. So let the red part is the desired string that I have to realize. And the red part I am moving up. So B can be realized by A. Now, what is our value is small a, capital A, B, C, D and E. These are our values. Correct. Now you check that small b here, you check that here capital A, small b and C, this deduction I can get from capital A. So capital A, small b and C, if I take capital A, small b and small c, these three I can get capital A, small b, small c I can get from capital A. Because this is a capital A generates capital A, small b, small c. So this generation is being done. What left we have? Small a, capital A, D and E. Correct. Now D can be realized by B. So here I am writing D can be realized by B. Perfect. Okay. D can be realized by B. Now what we have? A, capital B and E. So you check in the S, small a, capital B and E. So small a, capital B and small e can be realized from S. So that means I am approaching from bottom up. So this is a bottom up parser over which we can design. Correct. That means the same, that whatever the derivation I am making here, I am approaching in the bottom up manner. That will give us a bottom up parser. Correct. So here the two classifications are there, top down and bottom up. We mainly will be focusing on both the parsers will be focusing, but here our interest will be on LL1 parser. But shortly we will see why we should not approach with backtracking method. Okay. Now, first see that why we cannot consider the backtracking parser. This is the production rule pertaining to a grammar. S is generating RXD, RZD, X is generating, it is OA, or it is generating EA, and Z is generating A and I. correct? So this is the outcome of a production rules for a grammar. Let I have given a string s to realize this following string read. That means the first option is there. I have to start with the first production. If I start with R, X and D, or I can start with R, Z and D, both are fine because both are ending with R and D. R and D, these are the terminals. Only I have to expand X and Z. So I have two options. Either S can be expanded to R, X and D, or S can be expanded to R, Z and D. Now this X can be expanded to either AI, that means RAID rate, it is not possible. Z can be expanded to, sorry, X can be expanded to either OA or EA, correct? Here I have made a mistake. X can be expanded to either OA or EA. So OA is a possibility, or S is another possibility is there. I'm writing for this R, X and D, here EA. For Z, another possibility was AI. So Z is generating AI. So three different tree I am getting: ROAD road, RAID rate, and READ rate. Now, what is the problem? I was given a string S and a set of production rules. Now, when to get this string accepted, I check this R and D part. So I selected either this production or this production. That means two tree I had initially. Two tree means either this tree or I will be having this tree. This tree. Now once I start expanding X to OA, I find it out, no, the next character I need, it is E. So this is not a right derivation that I am following. This is not a right derivation. This is wrong. So that means I need to backtrack whatever the expansion I have given from here to again to X. So OA expansion, whatever the expansion we have given, we need to move back from that expansion to X again. That's why it is backtracking. And I am approaching with another extension, that is EA extension. So X is being given to EA. So it is right extension. This is right. So this is a backtracking part. So one backtracking is done here. Another backtracking was here. R and D was the matching that we could find it out in the string. Now Z was AI. Now AI was not expected. The next character was E and A. So that means again we have to backtrack from here. This is also a wrong strategy or wrong pathway that we had taken. Again we need to make a backtrack. So that is the reason that backtracking cannot be followed to get a string accepted. We need to formalize a rule so that I can move in a unit direction and can get a right result every time. Okay, that is the reason the backtracking method that was there to design a top-down parser was not being followed. We come into the area of non-backtracking, and in our next video lecture we will be moving into the LL1 parser and we will discuss the related parameters there. Okay, so if I summarize today's class, that we have gone through three things. One is operator precedence, another is operator associativity, another is classification of parser, and why we should not select backtracking method to design a top-down